At some point, everyone dreams of flying, to physically elevate themselves above their environment. And flight was a dream of mine when I was a kid, and this is what I do today. Hi, I'm John Harrington, NASA crew member of shuttle mission STS-113, and I'm also a member of the Chickasaw Nation of Oklahoma. Every culture and every civilization throughout recorded history has a mythology involving human flight. One of the best-known legends of human flight is the Greek story of Icarus, who tried to escape from an island prison by using wings made of wax and feathers. Icarus flew too close to the sun and the wax melted and he fell into the sea. Ancient Chinese records speak of human attempts to sail through the air by attaching themselves to kites. In today's pop culture, flight is common among comic book superheroes. And numerous Native American cultures celebrate flight in their traditional dances. But it was only about 100 years ago that the problems of powered flight were overcome and human beings finally took to the sky. In this episode of NASA Connect, host Jennifer Pulley will take you on a journey to find out how mankind first learned to fly. You'll discover some secrets to the Wright brothers' success 100 years ago. In your classroom, you'll build your own flying machines and evaluate their performance. You'll also learn how NASA engineers are developing new morphing technologies for the next century of flight. And you'll explore the web to follow in the footsteps of the Wrights with some cool interactive activities. All in this episode of NASA Connect.
I'm Jennifer Pulley, and welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. I'm here at the Wright Brothers National Memorial on the Outer Banks of North Carolina. This is where Orville and Wilbur Wright flew the first airplane 100 years ago.
I've read that there are many inventors besides the Wright brothers trying to invent the airplane.
Oh yeah, it's true. Many famous inventors, including Alexander Graham Bell, Thomas Edison, machine gun inventor Hiram Maxim, and Samuel Langley, the secretary of the Smithsonian Institution, had all attempted to build flying machines.
My teacher said that the Wright brothers didn't have high school diplomas and didn't have a lot of money to work with. Is that true?
They were both good students in school, and Wilbur completed all the courses he needed to in order to graduate high school. He just never picked up his degree. Both Wilbur and Orville loved to read outside the classroom. And you're right, they really didn't have a lot of money to work with. But the Wright brothers figured out how to conduct their experiments without spending a lot of money. They were able to support all their experiments through their day jobs, their small bicycle shop.
So how come it was the Wright brothers who invented the airplane?
You know, that's a good question. Why was it that these two little-known bicycle mechanics from Dayton, Ohio, succeeded, where so many other famous and successful inventors had failed? Well, to help find the answer to that question, we spoke with Dr. Tom Crouch, Senior Curator of the Division of Aeronautics at the National Air and Space Museum. Dr. Crouch, what was the Wright brothers' secret to success?
Jennifer, they were brilliant, intuitive engineers. In order to invent the airplane, they had to come up with a process of invention, a way to solve really difficult technical problems. Today we call it the engineering method. The first thing that the Wright brothers did correctly was to define the problem. The Wright brothers studied the experiments of other inventors and quickly realized that many of them were missing the true problem. The Wright brothers saw that the true problem would be maintaining balance and control in their machine. Many other experimenters were convinced that an airplane could only be successful if it relied on some method of automatic stability. They thought it would be impossible for a pilot to react quickly enough to all of the changes that might happen to an airplane in flight. They thought that it would be like balancing on the head of a pin, which is impossible to do. The Wright brothers saw things differently. They were bicycle builders and bicycle riders, and they drew on that experience when they thought about controlling an airplane. Imagine that you're trying to describe how you ride a bicycle to a Martian or to someone who's never seen one. You might talk about riding downhill on a tiny seat, perched atop two very narrow spinning tires, in addition to which you have these pedals you're going to have to work and a handlebar to steer with, and you're going to have to coordinate all of that at the same time.
You know, I can see how the person you were talking to would think they'd have to be the world's greatest acrobat to ride something like that.
That's right, but the Wright brothers knew that you internalized the business of riding a bicycle, and they also knew that the same thing would happen with an airplane. You would learn to fly an airplane and do it automatically.
So the Wright brothers then correctly defined the problem.
Yes, they knew that control was the problem, so the Wright brothers observed the movements of the soaring birds to see if they could figure out how they controlled themselves in the air. They thought they detected subtle ways that soaring birds altered their wings to maintain balance, but the Wrights were stumped as to how they could duplicate the organic movements of a bird's wing in a very mechanical flying machine.
Which brings us to the next step in the engineering method, propose solutions. Tom, what solutions did the Wright brothers propose?
They really struggled with how they could control the geometry of their wing to control the motion of the flying machine. Until one day, Wilbur was in the bicycle shop and a customer came in and asked for a bicycle tube for his tire. And Wilbur took it out in a box just like this one, and he was fiddling with the box, standing there talking, and it suddenly occurred to him that the answer to their problem was right in his hand. Wilbur noticed that if he put the thumb and forefinger of one hand on these two diagonal corners and the thumb and forefinger of the other hand on the opposite diagonal corners, that he could squeeze the box back and forth. He noticed that the box twisted. In his mind, Wilbur pictured the top and bottom of the box as the wings of a biplane. With a simple system of cables, he could draw the corners together, turning one set of wingtips up in the wind and the other set of wingtips down. He realized in this way he could control the shape of his wings and would be able to roll his aircraft in the sky.
Okay, so now the Wright brothers have a proposed solution: warp their biplane wings. Using the engineering method, the next step would be to evaluate their solution using tests and prototypes. In other words, the Wright brothers needed to put their wing warping theory to the test.
That's right, Jennifer. They didn't begin by building a powered flying machine. They had to start by building and testing prototypes. And they started with this small biplane kite. Watch how this prototype flies. Notice when you pull on the opposite strings, the kite rolls to the left and right. The wing twisting concept Wilbur proposed from the inner tube box actually worked in his prototype kite.
So from the success of their kite, the Wright brothers built the first powered airplane.
Now, first, they built a series of 3 gliders over 3 years, and what they learned helped them to build the world's first powered airplane.
Hey, that leads us to the final step in the engineering method: select and refine the best solution. And in order to learn how the Wright brothers refined and improved their flying machines, we're here at the Wright Experience Laboratory in Virginia. We're talking with Ken Hyde. He's the founder of the Wright Experience. Now, Ken, tell me, how did the Wright brothers improve upon their flying machine designs?
Well, with each new design and each new flight test, they did small refinements and small changes to their design. There may have been many problems at any given stage of the flying machine's development, but the Wrights only changed one thing at a time. They were never confused about which change was causing which results.
Ken, that makes sense. I mean, that way they could select the changes that worked and then continue to refine their design.
That's right. And Jennifer, this is the results of all their hard work. This is a flying reproduction of the Wright brothers' 1902 glider.
Ken, this is quite different from their original kite, isn't it?
Not really. It uses the same principle of wing warping and wing twisting that they used in the original kite. But what was so important and so radically different about this glider from their early designs was that the 1902 glider was the first aircraft ever that solved the problem of controlling an airplane in all 3 axes: pitch, roll, and yaw. Okay, Jennifer, this is a control for the elevator, which controls the pitch, which is the up and down movement of the aircraft. Control roll, I can shift the hip cradle back and forth. Watch how the wings twist. That would change the roll position of the aircraft during flight. But also wired into the hip cradle is a control for yaw. Watch how the tail moves at the same time as the wings are warping.
Ken, this is so cool, but can you really fly this?
Absolutely. We have a 1902 simulator that you can fly. Come on, I'll show you. Jennifer, this is our 1902 glider simulator, and it was developed from the wind tunnel test that we did on this machine. Bill Haddon is our expert on this, and he is a good instructor. He's going to check you out in this and tell you about the machine.
Great. Nice to meet you, Bill.
Hi, Jennifer.
Tell me about the simulator.
This was based on the wind tunnel numbers generated by taking our full-scale glider and putting it in the Langley full-scale tunnel in Hampton, Virginia, operated by Old Dominion University. And the results of the wind tunnel test were incorporated in Flight Simulator by Burrell Applied Research. That's their business, making flight simulators. So when you fly the simulator, you're flying actual wind tunnel data results. So that's a lot of fun. Would you like to try it?
I thought you'd never ask. I'd love to try it.
Okay. Okay, Jennifer, on the left, you see your airspeed in knots. That's 21 knots, 22. That's perfect right there. Airspeed control is critical. If you get too slow, it'll stall, and too fast, it can dive into the ground. It's just elevator control and hip cradle. When you move the hip cradle, you're warping the wings to control roll, and you're also getting rudder movement with it.
Well, it took some practice, and it wasn't real comfortable, but I think I got the hip thing and the elevator thing going. I was finally able to make a glide that lasted about 63 seconds. Oh, thank you so much, Bill.
You're welcome.
Well, how was it, Jennifer?
Oh, Ken, it was incredible. It was incredible. I'll tell you, it was a little uncomfortable, and it was kind of difficult to maneuver, but I can really relate to how the Wright brothers must have felt. They had a lot of stamina in order to be able to do this.
They sure did, and this 1902 glider, all of their innovations are in this machine, is what they were striving for. By 1903, the Wrights were ready to add an engine and propellers. The Wright brothers' breakthrough in propeller design came when they realized that a propeller was merely a wing in rotation in a helical pattern, creating lift in the forward direction. Once they saw the propeller in this way, they were able to use their wind tunnel data about lift and drag to design an efficient propeller. Jennifer, we also have a simulator of the 1903 Kitty Hawk flyer. Would you like to fly this machine?
Of course I would, Ken. Now, while I take flight on the 1903 flight simulator, why don't you check out how to build your own flying machine and test its performance?
Hi, we're students at Dunseith Indian Day School here at the Turtle Mountain Reservation in North Dakota. Yay!
In ancient America, our ancestors dreamt of flight, and we celebrate this dream through our dancers and stories, because American Indians have always been fascinated by the flight of the powerful eagle and the graceful butterfly.
NASA Connect asked Dunseith Indian Day School to show you this program's hands-on activity.
You can download a lesson guide and a list of materials from the NASA Connect website.
Here are the main objectives.
Students will predict the effect of kite sail area on kite flight, measure the base and height of a kite, use reflections to create kites, calculate area of a trapezoid, calculate aspect ratio, understand how early flight was influenced by kites.
Here are some terms you'll need to know.
The span of a kite is the widest distance from side to side. Aspect ratio is the ratio of the square of the span to the area of the kite. Drag is a force that pushes against an object and slows it down. Lift is the aerodynamic force that holds an airplane in the air.
Good morning, class. Today NASA has asked us to investigate the size of kite sails to determine how area and aspect ratio influence flight efficiency.
3 kites will be built using different measurements as outlined in the lesson guide. First, hold the long end of a piece of 8.5 by 11 sheet of paper and fold it in half. Starting at the fold, measure 3.5 centimeters along the top of the paper and mark point A. Now measure 9 centimeters along the bottom of the paper, measuring from the fold. Mark point B. Draw a line segment AB. Reflect the line segment AB across the fold line. Call the reflection of point A, A prime, and the reflection of point B, B prime. Draw a line segment A prime, B prime. Fold back along line segments AB and line A prime, B prime, forming the kite shape. Place a piece of tape firmly where line segment AB and A prime, B prime meet. Place a skewer stick along the span of the kite and tape down firmly along the entire length of the skewer stick. Cut off any excess. Tape a kite tail to the bottom of the kite sail where point B meets point B prime. Starting at the top of the flap, which is labeled point F, measure 7 centimeters down along the flap and 1 centimeter in from the fold. Mark and label point E, then punch a hole at point E. All measurements will be recorded onto the worksheet. You will calculate and record the kite sail area using the given formula. Area equals 1/2 the height times the sum of b sub 1 and b sub 2, where h is the height and b sub 1 and b sub 2 are the bases. Remember to multiply the value by 2 to calculate the sail area. You will also calculate and record the aspect ratio using the formula AR equals S squared divided by A, where S is the kite span and A is the kite sail area. Tie one end of the string to the hole and wind the other end onto a cardboard string winder. For the other two kites, repeat the same steps, adjusting the given values for point A and point B found in the educator's guide. Remember your reflection. Once you have completed your calculations, it is time to proceed to the outdoor test flight.
Teams, are you ready? Let's let them fly.
Yay! Perform 2 trials for each kite, rotating student roles until all 3 kites have completed their 2 trials.
There are 2 questions that we need to answer. How did the surface of the kite affect its flight? And was this effect significant?
Roger.
The smaller kite didn't have enough space here, surface area. This flew just right, had enough surface area. This did too much acrobatic.
What other factors could be changed to investigate the effect on kite flight?
Josh?
Weather, wind, tail, surface area, and weight.
When you complete this activity, discuss what improvements you would make to your design. A helpful tool is the interactive kite modeler from NASA Glenn Research Center. On this website, you can study the physics and math which describe the flight of a kite. You can choose from several types of kites and change the shape, size, and materials to produce your own design. By selecting the Field button, the kite flies with the control line running from you to the kite. Depending upon your choice, different variables are shown. The values of these variables are shown on the output panel. The kite modeler tells you if your design is stable or not, and also computes a prediction of how high your kite will fly. Teachers, if you would like help to perform the preceding kite building lesson, simply enlist the help of an AIAA mentor, who will be glad to assist your class in these activities. AIAA stands for the American Institute of Aeronautics and Astronautics.
Wow, Ken, this simulator for the 1903 flyer is so different from the simulator for the 1902 flyer.
It really is.
Oh, thank you so much.
Thank you.
Okay, let's review. So far, we've learned how civilizations throughout history have dreamt of flight. We've seen how the engineering method can be used for solving complex problems and making dreams a reality. And you've applied a bit of the engineering method yourself by building kites and evaluating their performance. So what does all this have to do with NASA today? Well, Anna McGowan at NASA Langley Research Center in Hampton, Virginia has the scoop.
How can biology be helpful in designing aircraft?
What is the relationship between pressure and force? Why are the computer simulations important to the aircraft design process?
The Wright brothers discovered ways to sustain controlled flight. Today at NASA, the challenge is to research ways to make flight safer and more efficient.
One piece of research NASA is doing is called the Morphing Project. The Morphing Project is part of the next generation of breakthrough vehicle technologies. It's about designing the airplane of tomorrow and changing the world again in the process, much like the Wright brothers' invention changed the world they lived in.
We got the word morphing from the word metamorphosis. The word morph means to change, and we're using a lot of advanced materials and technologies to research how to make airplanes change from one configuration to the other. That's what engineers and scientists in NASA's Morphing Project are trying to do, transform the future of flight.
How are you transforming the future of flight?
That's a great question. The Wright brothers were inspired by watching birds soar,
and they designed their airplanes with wings that could manipulate the wind. The Wrights didn't use flaps on their machines like airplanes have today. In the Morphing Project, we were working on making airplanes as versatile as a bird is. So we're taking some lessons learned from nature, just like the Wright brothers did.
We're researching and testing many advanced technologies. One area is called smart materials.
We call these materials smart materials because unlike traditional materials, these materials actually move when you apply a stimulus like voltage or heat. They're similar to muscle tissue in this way, So instead of using complicated mechanical gears to move or control parts of future airplanes, NASA is looking at using these smart materials as future control devices on airplanes.
Another advanced technology that we're studying is called adaptive structures. In studying the structures for future flight, we're actually looking at technologies that can change the shape of parts of the wing during flight.
Why do you want to change the shape of the wings during flight?
Well, all wings must be able to adapt to different flight conditions.
Birds do this by gently bending and twisting their wings while they fly. In today's airplanes, we're using flaps and slats to adjust the wings to different flight conditions. In the future, we're hoping to enable wings to gently change shape in many different ways, similar to birds.
This is one example of an adaptive structure that we're working on. This wing changes shape for different flight conditions. It's designed very different than today's airplane wings. Today's airplane wings are typically hollow to hold fuel, and they're also very stiff.
This adaptive wing instead has a center spine to carry most of the aerodynamic load and movable ribs to change shape during flight. We design airplane wings using the principle of pressure. The following algebraic equation should help you understand this principle. Pressure is defined as the force divided by the area over which the force acts. The force in this case is the aerodynamic load. Have you ever popped a balloon with a nail? It's pretty easy to pop the balloon with one nail because the force applied to the balloon is acting over a very small area, only the head of the nail. This means very large pressure. Now, if you try to pop the same balloon with a bed of nails applying the same amount of force, you notice the balloon is very difficult to pop.
Why is that?
Because the area of the bed of nails is much larger than the area of the single nail. If we refer back to the equation for pressure, if you keep the same force applied but increase the area, pressure actually becomes much lower.
With this adaptive wing, we want to make sure the force, or the aerodynamic load, is distributed evenly across the wing, preventing the wing from breaking. We actually call this adaptive wing here the fishbone wing because it resembles the spine and ribs of a fish. To understand and design the fishbone wing, the engineers here at NASA use advanced computer simulations. These computer simulations help us understand the mechanics of the fishbone wing and tell us how the wing will perform in real life. We are even looking at new ways to control the airflow over the wings of future airplanes. The study of airflow is called aerodynamics, and today's airplanes use large flaps to control aerodynamics. For future airplanes, we're developing technologies that use very small devices to control the airflow on airplanes. We call this micro flow control. For example, tiny fluctuating jets that create a small plume of air on the surface of the wing can be used to make the flow smoother and less turbulent, and this reduces drag. By reducing drag, we can save on fuel costs and also reduce the amount of pollution coming from the airplane engines. Here's an example of one of these jets. This device would suck in air and blow out air very rapidly to control the airflow over the wing. Now, several of these devices would be placed in a wing to control the airflow over an entire wing. Even this example is similar to how a bird flies. In addition to twisting and bending their wings in flight, birds also rely on their feathers to adjust the airflow over their wings. Finally, we're applying the principle of biomimetics in the morphing project.
Bio what?
Biomimetics is the abstraction of good design from nature. In other words, you look at how nature works for maximum achievement at minimal effort.
Today we're even examining the shape of fish fins because, in a way, fish are flying through the water.
Here are several examples of different fish fins that we're studying. We actually work with marine biologists to understand how the fish swim and how they're really efficient flyers. We also study seagulls. Seagulls can soar really well, and their unique wing shape is one of the many reasons they fly so efficiently. Here is an example of a wing that we would actually design for wind tunnel testing. We call this the hyper-elliptical cambered span. because of the really unique shape and because we use ellipses to design this wing. In the morphing project, we take lessons learned not only from biology, but we also use a lot of advanced technologies, new math, new approaches, and new science to really make future airplanes even safer than they are today. We also want to make them more capable and able to fly in new and different ways. We also want to make them more efficient to help with pollution and also reduce the cost of flying. NASA's morphing project is looking to the future and trying to transform the future of flight.
Thanks, Anna. Now it's time for a cue card review. How can biology be helpful in designing aircraft? What is the relationship between pressure and force? Why are computer simulations important in the aircraft design process? If you're watching this on videotape, you'll want to pause the tape to discuss these questions. Okay, did you get all that? So far, we've seen how the Wright brothers began powered flight for humans, and we've seen how NASA is working to apply some of the early principles of flight that the Wright brothers perfected. You know, aeronautics sure has seen a lot of changes in the last 100 years. Let's visit Dan Giroux at his web domain.
Hi, and welcome to my domain. The U.S. Centennial Flight Commission was created by the U.S. Congress to serve as a national and international source of information about activities to commemorate the centennial of the first powered flight. On this site, you can learn about America's plans for celebrating the 100th anniversary of the first Wright brother flight. Check out the Sights and Sounds section, where you'll see pictures and download movies. There are hot links to cool websites about aeronautics and astronautics. This site is a repository for many things related to the Wrights. For educators, there are several links to activities that encourage educators and students to explore the Wright brothers' flight experiments and to research, plan, and participate in your own centennial of flight activities and events. There are also cool downloads for posters featuring famous firsts and spectacular images from aviation history to present day. And now, back to you, Jennifer.
Well, that wraps up another episode of NASA Connect. We'd like to thank everyone who helped make this program possible. Got a comment, question, or suggestion? Email them to connect@lark.nasa.gov or pick up a pen and mail them to NASA Connect, NASA's Center for Distance Learning, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia 23681. Teachers, if you would like a videotape of this program and the accompanying lesson guide, check out the NASA Connect website. So until next time, stay connected to math, science, technology, and NASA. See you then.
Captioning funded by the NAC Foundation of America.